Now, the different types of statistics. There are three types of statistics. First is Maxwell Boltzmann statistics. Second one, Bose Einstein statistics, and the third one is Fermi Dirac statistics. Now, first we'll consider this one, Maxwell Boltzmann statistics. The Maxwell Boltzmann statistics, it is the classical case, but Bose Einstein and Fermi Dirac are the quantum case. Now see, classical case means the particles are distinguishable. Suppose we can that means we can distinguish them. Suppose I have three particles. I can identify them 1, 2, 3, and I can distinguish them. Now in quantum mechanics, if I have three particles, then I cannot number them like 1, 2, 3, because all of them are same. It's very difficult to distinguish. Now see, it is a classical case. In this case, the particles are considered to be distinguishable, and any number of particles can be put in the same single particle state. That means we can put any number of particles in the same state. This classical description imposes no symmetry requirements on the wave function. I had told you before that we have two types of wave function. One is symmetric and another is antisymmetric. But in the case of classical, there is no symmetry requirements. That means no symmetric, no antisymmetric. When two particles are interchanged, see, there is no symmetry requirements on the wave functions when two particles are interchanged. See, if one is state, here I have a particle, and here if I interchange both of them, like, then there is no symmetry requirement. The particles are then said to obey Maxwell Boltzmann statistics, in short MB statistics. Example, the molecules of a gas. Now come to the second type, Bose Einstein statistics. Now Bose Einstein statistics, particles with integral spin. That means the particles which obey Bose Einstein statistics, that particle have integral spin. This is the case where each particle has a total spin angular momentum which is integral. It is 0, 1, 2 integral spin angular momentum. Example, helium-4 atoms or photons. The total wave function psi is symmetric under interchange of any two particles. See, if I have two particles, here 1, 2, and 2, 1. Okay, now the wave function of this is, suppose q1, q2. Q is the position. If I take the position here q1, here q2. Now here q2, here q1. Now this is, when you interchange the particles, the function becomes psi q1, q2. It means when we interchange the two particles, the wave function remains same. See, psi dot 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 qi dot 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 qj. I means the ith particle. The q means position of that particle, qj. And when you interchange, when you take first qj and then qi, then see, the wave functions remain same. There is no change in the wave function under interchange of two particles. Equation number 1. The interchange of the two particles does not lead to a new state of the whole gas. Since when we interchange the two particles, since the wave function does not change, that means we cannot get a new state. Wave function does not change means the state is same. The particles are indistinguishable. Since it's a quantum case, so particles are indistinguishable. There is no restriction on how many particles can be in any one single particle state. See, the particles which have integral spin, that there is no restriction on how many particles I can put in a single state. I have told you before. Then particles satisfying the symmetry requirement 1 means this one. symmetry requirement 1 are said to obey Bose Einstein statistics, and in short BE statistics, and are sometimes called bosons. Okay. Now come to the third one, Fermi Dirac statistics. In Fermi Dirac, the particles which obey Fermi Dirac statistics have half integral spin. Okay. This is applicable when each particle has a total spin angular momentum which is half integral. Half integral means 1 by 2, 3 by 2, ... The examples of these types of particle are electrons, helium-3 atoms, etc. The total wave function psi is antisymmetric under interchange of any two particles. That means in this case, if I interchange two particles, this is 1, 2. Here one particle and here two particle, position coordinate 1, 2. Now suppose the wave function psi q1, q2. Now if I interchange this, if I take two here and 1, 2, this position coordinate q2 and position coordinate q1. Now the wave function of this states minus psi q1 comma q2. See, when we interchange the two particles, the wave function changes its sign. See, two particles qj and qi, when I interchange, first I take qi and then last qj, then here 1 minus sign comes, means the wave functions become antisymmetric. The interchange of two particles does not lead to a new state of the whole gas. See, since we know that the particles are indistinguishable. Why it's indistinguishable? Because it's a quantum case. So when we interchange the two particles, see these two, this is indistinguishable, means 1 and 2 are same. We cannot distinguish. If I interchange also, I cannot distinguish them. So on interchanging, we cannot get a new state. The particles are indistinguishable. Suppose that two particles I and j both are in the same single particle state. Now come to next point. There is a big question. See, now this gone. Now if I take two particles I and j in the same single particle state, are interchanged. Suppose if I take here, suppose if I take a same single A state and I take here two particles in one state. See, if I take two particles, suppose one and another particle, two particles, and the wave function of this is psi, right? If I take a position coordinate q1 and q2, psi q1 q2, right? Now in the same state, if I take two in the first and one in the last, then it's same. Since it is in the same state only, so when we interchange, there is no minus and nothing. If I take in the different state, suppose here 1 and 2, 1 and number particle 2 and here 1, then only what happen, the wave function changes. But in the same state, there is no change in the wave function. See, qj, if I take qi first also, there is no change in the wave function. Number 2, since the fundamental symmetry requirement 1 must also be valid. See, but here our symmetry requirement condition. Now if I apply equation 1 into equation 2, what happens? I'll get psi equal 0. When particles I and j are in the same state, psi equal 0. Psi equal 0 means what? See, here we took I and j are in the same state. Now after taking, if I apply equation 1 into equation 2, then what happens? See, psi ... qi qj. Now this one, psi qi qj means minus psi qj qi. If I put here minus psi, here, see, equation 2, here, this one, psi ... qj qi means what? Minus psi qi qj, minus psi qi qj equal psi Qi Qj. Qi Qj. Now if I take this to that side, then minus 2 psi Qi Qj equal 0 means psi Qi Qj equal to 0. See. So psi equal 0. Psi equal 0. See, psi equal 0. That means when we put two particles in the same state, the wave function is equal to 0. Thus, in the Fermi Dirac case, there exists no state of the whole gas for which two or more particles are in the same single particle state. This is the so-called Pauli exclusion principle. See, that means in the Fermi Dirac case, we cannot put more than one particle in a same state. See, here we put two particles, and our result is that psi is equal to 0. That means wave function is equal to 0, which means it's invalid. That means we cannot put two particles in a same state, and this is the Pauli exclusion principle. The restriction that there can never be more than one particle in any given single particle state. Particles satisfying the antisymmetry requirement 1 are said to obey Fermi Dirac statistics and are sometimes called fermions.